In this section, section 1.4, we'll talk about piecewise functions, or basically functions that are composed of more than one function, as you can see in this example. For example, now note that this point where the transition occurs, or where the change occurs, essentially x equals 0 in the example right here, we'll call it the transition point. This is where the function changes its definition. So you can graph these by hand. You can basically create a table for each piece, or you can use a graphing calculator, or you can also use Desmos. So I included the link to a video how to create a graph with your TI-84 or a graphing calculator. So you can do it in one of two ways. Basically, the idea is that you multiply each function, put it in parentheses like that, by its condition. And how you can find these inequality symbols, you can press second on your calculator and math if you're using a graphing calculator. That'll take you to the test menu and you should be able to see the inequalities. So you can do it in one line with using a plus, or sometimes it doesn't work, or maybe it's hard to see the whole definition if you make a mistake. So you can do it as two different functions like this, and then you should be able to see it. The one downside of using a graphing calculator or Desmos is that it does not show you whether it's a whole or a filled-in value at certain points. For example, if the two pieces do not match, then one piece with a strict inequality, for example the x plus 2 for our example, that would create a whole. Basically the y value does not exist there, and a filled-in point for the piece with inequality with greater than or equal to or less than or equal to. But if the two pieces match, then essentially that whole gets covered up. But again, we can do this by hand. Let's take a look at what the graph looks like. You can also graph it in Desmos. It's very easy to do it, and you can also see the colored version of your graph. The code is a little bit different. Locate these braces that actually conveniently close for you as well. So you use the set brackets, and then you would basically type in the inequality first with a colon, followed by the function, comma, the next inequality. You basically can do greater than and then equal sign, unless you're using an app on your iPhone or iDevice. I don't know if it's available on Android, but again, you can also use it in the web browser if you do not see the app. So you can do greater than or equal to, which will automatically switch to greater than or equal to sign for yourself. So I did use Desmos. This is what the graph looks like. If you note, I actually drew the whole and I drew the filled-in point. Again, the reason for the whole, because we have strictly x less than 0, but we still end up with x equals 0. So let me show you how to create a table for each piece real quick. So for example, for us, it was, let me make sure I can draw, just a second. Okay. Sorry, a little trouble with my tablet here, but I think it's working now. So the first piece will be y equals x plus 2, and we can create a table. To do this by hand, how would you do this? Basically pick any values that are less than 0, say -2, -1, but you may want to finish at 0, because even if it's less than, we may have a whole, but we may still have a value there. So you may have -2 plus 2, that's 0, -1 plus 2, that's 1, and 0 plus 2 is 2. So notice we have these points right here and right here, and then you end up with a whole. Okay, and then similarly we can do this on the other side with y equals 2x minus 1. That's the second line, and the table that you can create here. Basically now, again, start with 0, the transition point, and then maybe plug in a couple of values that are greater than 0. So at 0 we'll have -1, which notice it's right here, and then at 1 maybe we'll get looks like 1, and at 2 it looks like we'll get 3. So point right here, and then maybe at 2 is right here. So as you notice, the second line rises quite a bit faster. It has slope 2. So again, then you have to supply the hole and the filled in point where they do not match. Now, here are some more examples. Let's say if we have the second function, x, if x is greater than or equal to 2, and 2 if x is less than 2. So we have to find some y values first. So how I did that, basically, it's just knowing where to plug in. The f of 1, let's check on our condition. 1 is less than 2, so it's going to be this constant 2 right here, which is why we got 2. Now f of 2, so that's exactly 2. Now with the condition that satisfies us is x is greater than or equal to 2. Now we have to plug in the value inside the x, this one. So 2 also happens to equal to itself. And 3, the same thing. 3 is greater than or equal to 2, so we plug in into the x and we get 3. So you have to verify which section the x goes into. Basically check your condition, whether it's less than the transition point or exactly equals to, or and so on. So here's what the graph looks like. So notice it's a constant 2 all the way up to 2 ending with a hole, but then the filled in point also happens to be 2. So notice how because its x is also 2, so the filled in point covers up the hole. So there is really no hole at that point. So be careful, some of your homeworks they may show a hole, but if the two pieces coincide, the filled in point essentially falls right on top of the hole and covers up the hole. And then so that's how we graph it. Again, I used it. Let's go back to the graph real quick. You don't need too much of a table here because it's y equals 2 no matter what. On the left hand side, let me write this. So it's y equals 2. So notice how we had a constant here, but then it's y equals x, starting with a table at 2 and so on. So notice how at 2 is also 2, at 3 it's 3, at 4 it's 4. So you can graph this by hand. So let's keep going to the next one. So what if our function was 1 if x is greater than 0 and negative 1 if x is less than 0? Now notice it could be that both inequalities are strict. Essentially x equals 0 is not included in the domain of the function, which can happen, so the transition point is missing. But we can still graph this. So how do we find the y values? F of negative 15 and f of 12. Well, same idea. F of negative 15 is less than 0, so the y value would be negative 1. F of 12, on the other hand, is greater than 0, so the y value would be 1. So it's only two possibilities then, except for x equals 0. So how does the graph look like? Again, if x is less than 0, it's basically constant negative 1 going to the left. If x is greater than 0, it's positive 1 going to the right. Again, it's hard to see, but this is actually negative 1 and this is 1. And so we have a hole at both points. We do not have a filled in point here because x cannot equal to 0. So the y value is missing because of our definition. So the domain is basically everything except the 0. That's why we have parentheses here. 0 is not included. You can also write it in the set notation, but I think I wrote it how it would be on the homework as well. So everything but 0. And the range is only two y values, so it's negative 1 and positive 1 in this case. And that's it. And one more, sketch the graph. What if we had f of x equals to x squared? It doesn't have to be a line. If x is greater than or equal to 2, and then 3x minus 2 if x is less than 2. So notice x equals 2 is the transition point. It is included for the x squared. So again, the whole gets covered up. Again, how we can check? Again, you have two pieces. You have y equals to 3x minus 2 on the left because it's for any x that's less than 2. So again, you can create a quick table. You can try 0, 1, 2, for example. But you want to know what's happening at the transition point. So at 0, we have negative 2. At 1, it looks like we have positive 1, and at 2, 2 times 3 is 6, minus 2 is 4. So the transition point, the y value is 4, which is right here. But we also have y equals x squared on the right. So again, we can create a table, x, y. Again, let's start with a transition point, but if we plug in into x squared, we'll get 4. So the y values happen to coincide, which is why, again, we have just a filled-in point. And this seems like a line, but it's really x squared. It's just starting to grow pretty fast at this case. So this is how Desmos shows up. But again, it looks a little bit linear, but it is quadratic actually. So it's a piece of a parabola. And then you can draw it. So what's the domain? In this case, the domain is all real numbers because everything including the transition point, which is x equals 2, it's included in the first piece, so everything is included. The range is also all real numbers because, again, all the y values are included. This looks like actually a continuous function, but even if it's not continuous, every y value is covered. So you can take a look at the graph and tell the domain and range. And one more question. Here is kind of an interesting question where in calculus you'll explore this a bit more, wherein the function does not have a break or discontinuity. So say here is x squared plus 2 if x is less or equal to 1, but it's ax with some constant a if x is greater than 1. So the question is, will it have a break at x equals 1 unless a is equal to what? So here is a question mark. We don't know what. Well, how we can check? Let's check what it equals to in the first piece, x squared plus 2. We can plug it in, and so we'll get positive 3. That means that in order for it not to have a break, the second piece, which is ax equals, also has to equal to the same y value, 3, at x equals 1. So how can we solve for a? Well, if x is 1, then we can plug in. It's going to be a times x, which is a times 1, equals to 3. Well, that means that a is also 3. So in this case, the function is not going to have a break because we know that it's going to be a equals 3. And all the other values for all the other values of a, it would have a break. And that's it for this section.